So thank you all for coming. Again, before I start, let me just help me actually meet my audience a bit. So is anybody here familiar with recommendation systems? Machine learning? Math? Okay, cool. Cool. I'll be talking about recommendation systems, but before I get to that, I'll give you some basics in math, and all you will need to understand that is just to remain awake, because I'll start with the basics and build up slowly over time. Now, one really interesting thing that fascinated myself, and obviously if you never worked with recommendation systems, you might have not heard it, but recommendation systems as a niche of machine learning were pretty much in the dark ages for forever, pretty much. That is, until one company actually started the whole revolution, so to say. So does anybody have any idea which company that might be? Who said it? Yeah. so believe it or not, but actually until 2006, like there was a bunch of research on the topic of like classification and predictions and whatever, but recommendation system, it wasn't an interesting area. And in 2006, Netflix actually announced like a $1 million prize for anybody who could come up with an algorithm that has better recommendations than their own algorithm. And it took 3 years actually for the winner to be announced, but the winning actually algorithm won by, I think, this is really like making me nervous. Maybe it's better. so basically the winning algorithm actually outperformed their original algorithm by 10%. And it was actually a combination of algorithms that were developed over the time, and one of them, based on matrix factorization methods, I will mention today, so pay attention for it. Now, if you've attended my keynote speech today, I hope some of you did, you might have noticed that I became a father recently, and with all the fun moments it brings and stuff like that, there was one really interesting moment with our kiddo, and basically my wife was holding him in front of her head, and he was looking like he was staring directly into her, and I was like, Jesus Christ, this is one really intelligent kid, like look at that intelligence in his eyes. He just radiates the magnificence or whatever. He understands that he was like a month old or whatever at the time. And at that moment, he actually tried sucking on my wife's nose, like he pulled in and he was like, what the hell is this, So basically I was like, this is actually a dumbass, Now, the reason why I'm talking about this is, babies are one of the best examples of pattern matching mechanisms, believe it or not. Like they're born with some predetermined pattern matching mechanisms, like everything that looks like a tit, you should suck on it because some of it might give you some nutrition, But it also kind of shows you in a very interesting way that their pattern matching mechanisms, I mean, evolution is so wrong because they're so stupid when they're born, they can't even walk, they can't do anything. They can really, their pattern matching is really on a basic level. And why I'm saying that, well, basically the whole point of machine learning and everything in machine learning actually boils down to pattern matching. And basically you put some pattern on the input and you have something useful like suck or don't suck on the output. And basically if evolution has been wrong for such a long time, I think you can get away with basically being a bit wrong in the beginning of whatever you're building with, if you're building anything with machine learning. Now, on the other hand, a really cool thing, and this should hopefully encourage you, a really cool thing is that you can really get a seriously long way without having absolutely any idea what you're doing. Like you can just write some stuff up, put some data in, get some results. Those results might actually make sense, and you might present something useful to your boss, and it might actually bring some benefits, So it's machine learning in general can be quite rewarding experience. Now, one thing that I forgot to mention, which kind of builds up on this, is why I'm talking so much about machine learning. My day job has nothing to do with machine learning, But again, if you attended the keynote, I mentioned that I did my master's degree, and I actually did it in data science. So just realized that one purpose of my master's degree might be to actually talk about something that I learned there. So that's pretty much the only purpose so far I actually found of it, plus some basic stuff that we built. Now, speaking of pattern matching, I mean, I said that babies are stupid, you know. I mean, they are born, they're really new to this world, they have a tough time, you know, but I mean, it can be tough for people as well. I mean, like it took you at least, I don't know, 5 seconds, 3 seconds to actually understand that you're looking at a horse and a dog, right? So if you haven't figured it out, yes, there is a dog and there is a horse in this image. So even we as people can have issues with recognizing stuff. And don't even get me started with you know, like fried chicken and puppies, you know? I mean, like try quickly like figuring out which one is which, right? So it's a tough job. And even grown-ups can have issues with it. So my point being, don't be so hard on yourself. It takes time to actually improve things, but my presentation will actually give you some basics, well, some fundamentals plus some advanced things that you can really use to learn quite some cool things to work with. Now, why PHP 8? I mean, whenever you hear about machine learning, it's usually Python, might be Java, I never tried it, but I've heard that Java has even a library for machine learning. There might be some R. R is actually a pretty great language for machine learning, but why PHP? I was actually, I made a bet with myself because I never understood why is PHP not used for machine learning. Like, what is preventing it from being used for machine learning? I mean, it's not like Python is advanced in any other level except for the ecosystem, believe it or not. And what I actually figured out is that the only reason for PHP not being so popular is that it's actually missing an ecosystem. And this could be a call actually to some people might be interested to help this ecosystem grow, and I'm hoping to see it maybe improve over time. I mean, there are some downsides, as you will see. I got frustrated along the way because there really are some issues that are basically Python, for example, have some really great libraries, but that's it. Like, it's only about the libraries. It's not like about the underlying technology, you know. It's just a libraries thing. But PHP has 2 really great libraries. One is RubixML, and another one is PHPML. I would advise you to check the second one just for the sake of checking it, because I think it's a single author, and it's quite cool as a learning reference. But in this talk, I will actually focus on RubixML. And RubixML is extremely sophisticated and advanced and machine learning library for PHP, written in PHP, but it has some extensions done in C for, you know, like for some matrix stuff to make it a bit faster and use multiple cores and stuff like that. But I was actually quite surprised when I found it because I had no idea about it. And the documentation is amazing, the library is amazing, it's extremely intuitive, as you will see. But, like as I said, it's easy to talk, well, you just write this code, blah, blah. Let's actually understand how it all works. Because I think once you grasp how it all works, building stuff on top of that, you know, like usually people say, well, what about TensorFlow? I mean, Jesus Christ, did you listen to what I was talking about? It's the same thing with some advanced libraries. So I'd like to introduce you to some basics, and I think this basic, I mean, most of you have heard of, right? Vectors. Now, depending on who you ask, like, is it a math student or a physics student? Like physics student would tell you that, well, it's an arrow with a direction and whatever, velocity, blah, blah. If you ask a math student, vector is an ordered list of numbers, and basically we will be focusing on what math student says. So in this case, we will be talking about vectors as ordered arrays ordered arrays of numbers, so to speak. Now, what's also interesting, and I had to look this up every time, there are tons of different names, just for the sake of confusing people. There are tons of different names for vectors used along the rainbow of libraries. And you might have heard of them, like 1D arrays, rows, observations, samples, tensors, instances. These are all absolutely the same names, different names for absolutely the one same thing. It's a vector, you know, but I don't know, people like to play smart or whatever and confuse others. But basically, these are all the same names. And why are vectors important? Vectors are important because everything in machine learning boils down to you have to make a vector, and you use a vector as an input to your black box, which is something that does some prediction, and you get some output, whatever you want, like classification, clustering, whatever. But again, we'll get to that. So vectors. Now, basic high school or elementary school, whatever. One-dimensional vectors. It's just, you know, like one dimension, one feature, whatever. Basically two. You can graph it, like you can represent it visually by putting it on a single axis. You know, like I guess everybody's familiar with this. If you go to 2 dimensions, things get a bit more, I mean, interesting, but it's still understandable, right? So you have like 2 coordinates, 2 features, two whatever, two columns. We can go to 3 dimensions as well, right? I mean, it follows the same protocol. But the problem is, past the 3 dimensions, it actually becomes a bit of an issue to display stuff. I mean, you can use colors and stuff like that, but visual representing stuff above 3 dimensions is a bit, let's say, more challenging for humans. But funny thing is that mathematically speaking, it doesn't make any difference in, like when you're working with vectors in math, all the rules that I apply in 3 dimensions apply in like 100 or 100 million dimensions. It doesn't make any difference. Everything is the same, right? So it's just about the representation goes up to 3 dimensions. The rest is, the rest is yeah, stays the same. Now, I'll focus on 2 dimensions just for the sake, because it's easier to show, to visually understand it. So we have the vector A with coordinates 2 and 2, and we have vector B with another coordinates. Now, if I were to ask you how similar these vectors are, how would you answer, actually? Any ideas? Like, how similar these 2 are? You can use words. I mean, I'll help you. You can use words, but they look similar, and yet they're a bit different, so, but they seem to be pointing in a similar direction. So if these were 2 people telling me where the Hauptbahnhof is or whatever, I would probably find the way, right? So they're probably pointing in a similar direction, but again, they're not telling me exactly the same things, or they're not exactly the same. So that works, but it's not really mathematically precise. So there are tons of better ways, but one of those ways is actually really simple, and it's based on the angle between these 2 vectors, you know. And one metric that is really useful for measuring this similarity is actually cosine similarity. Like, you measure the cosine, and basically, based on that, you see, you know, like if cosine similarity is 1, they're similar. If it's -1, they're completely opposite. If it's, I don't know, 0, they are orthogonal, or whatever it's called. You get the idea. Everything that we will be talking about, and everything in machine learning, boils down to pretty much how you compare vectors. It's just that you go, I don't know, like to 100 million dimensions. You know, it's not 2 dimensions, but it boils down to finding similar vectors, and once you find some similar vectors, you say it's a puppy or a fried chicken or whatever, or stuff like that, you know, like those kinds of things. Now, you mentioned, did anybody ever try playing with machine learning? Like, even read anything about it? Yeah, I see 1, 2, yeah, cool. So whoever did, you probably encountered this iris species data set. So basically, there was some guy, I think he was a biologist or whatever, and basically he just went and found this iris flower, and he realized there seemed to be 3 different species of this flower, like setosa, versicolor, and virginica. I'll never get the naming right. So he figured out there are 3 different types of this flower, and the best way to actually figure out which species is, like, to figure out the species of the flower you have at hand is to actually measure the petal and sepal length and width, which are like these dimensions. And he just put it in an Excel or whatever, like CSV, I don't know, and he created a table out of it. And this is used for a lot of examples because it's like super simple, but it showcases everything that you need to know for pretty much anything. So basically, he figured out that with 4 dimensions, you can pretty much easily identify the family of this flower. Now, what you see here, I mean, you can immediately spot like the naming. I mean, samples, instances, observations, and the columns are called features, inputs, attributes, whatever, blah, blah. It makes me go insane. So I'll just stick to features as the columns, and the rows I'll call vectors, because that's what these are. Like each row is actually one vector. You can't really project it because it's 4-dimensional, but just it's still a vector. And another important thing that you need to know is that this kind of data representation is called dataset, because it's a set of data, you know. And usually the observations or vectors are usually unique. They not necessarily, but are usually unique. And why am I saying this? Well, because I think this is the only thing that's true amongst all libraries that I've encountered. They all seem to call this data set. Everything else is different. But this seems to be the only thing where they managed to agree. Let's call the list of data set. Now, how does this work in PHP? Believe it or not, it's actually extremely simple using Rubik's ML, believe it or not. So you can download the data set, and you can actually, I mean, it's actually like 1 line, 2 lines. Oh, the rest is just a logger. You can really easily just load the data set, and basically Rubik's ML gives you this data set object, right? Now, I mentioned cosine similarity before, because I told you that the best way to measure like similarity between vectors, and if you go back, like what we really wanted to do is, based on the input data, we want to figure out, like, based on the dimensions, like these. Let me see if this works. No. Perfect. Based on the dimensions on the input, we want to usually label, like figure out the label, like which species does it belong to. And I told you that cosine similarity is one of the easiest ways, one of the easy ways to do that. And it might sound a bit, I don't know, challenging if you check the formula for similarity between 2 vectors. You know, if you never encountered it, it's, well, what is this? But it's actually really simple. If you have 2 vectors, as we had before, A and B, measuring the cosine similarity between them is actually quite easy. It boils down to this. And basically you can see that, well, they seem to be 86% similar, right? So it's not like, well, it seems to be similar. No, this is exactly how similar they are. You know, they're like almost similar, but not exactly, right? Now, cosine similarity is just one way of measuring the similarity between vectors. There are other, you might have heard of some of them, you know, like Euclidean, Manhattan, whatever. And Rubik's ML has like tons of them. If you open the documentation, there's like tons of metrics. Each metric seems to be better for something else. I can't even tell you what is better for what. It's best. Usually you either experiment or you read some white paper that tells you, well, this metric seems to be the best for this use case with this data, whatever. But the point is, it all boils down to mathematical ways of finding how similar the vectors are, right? Now, back to our example with iris species. So, if I were to ask you, like, which vectors are similar to which, right? Like, how would you categorize them as what belongs to which species? There is, I mean, you can measure cosine for each, blah, blah, but there is one better and more reliable way of doing that, which boils down to cosine similarity, and it's called KNN, K nearest neighbors. Anybody heard of that one? 2? Cool, okay. K nearest neighbors. It might, usually when you see stuff like N something, K something, it usually, like it can be like, what the hell does this mean? But it's actually pretty similar, pretty simple. It boils down to basically you're as good as your neighbor is. You know, like you're most likely similar to whoever you are hanging out with. And basically, this is something that KNN algorithm boils down to. And to understand it, let me show you something. So if you look at this image, I mean, it takes you like what, less than a second to figure out who's sitting with who's part of which group, right? And how do you do that? Well, you do that by basically measuring how distance, like people sitting closer together are probably part of the same group, right? Well, turns out it's pretty simple. If you think about these people as two-dimensional vectors, you know, like intelligence and sex, for example, if you think about them as two-dimensional vectors, and if I were to give you a point, like this green one, and I ask you, based on where it is in this two-dimensional space, to which group does it belong to, I can say, well, I look at 3 nearest neighbors, and basically I see that 2 of the neighbors are blue, and 1 is green, and 1 is, orange. So basically, most likely, this vector belongs to the blue group, right? That's KNN. It's quite simple, and believe it or not, it's extremely easy in PHP. Like, you instantiate the class, you say how many nearest neighbors you want to find. Basically, in this case, is 3. And by default, it actually uses the Euclidean distance as a metric. I have no idea why. Somebody just figured that's a better way for whatever reason. But I'll use the cosine distance here. But it's actually, it just shows you that it's, sorry, here actually. It shows you that it's quite simple to change the kernel that you use for the distance, right? Now, so basically we have a data set, we have our estimator that we will actually feed with the data, and later on we will ask him, like, here is a vector, tell me to which species it belongs, the vector belongs to. All that is left is to train your model. You know, pretty much like do something inside which I'll talk about and basically figure out how to categorize the input vectors. And this is all PHP again. I mean, as I told you, like it's just that simple as that. Now, before I jump to what training model means, I'll just go back and if you check here, I'm not sure why it's not highlighted, you might have noticed there is a test data here. So basically the thing is, whenever you're training your model and what you want, you usually have like a limited set of data, of known data, and basically you want to use part of that data to, you know, like to feed your model, to improve it, and you want to use the rest to actually check how good or bad your model is, right? So this actually just takes the 10 samples, like puts them on the side and uses the remaining whatever it is, I don't know, like 100 or whatever, 90, I don't know, to train your model. And visually speaking, this is all it does, right? So basically, you take part of your set for training and the rest for testing the data. Now, I told you about training, right? So what exactly is training? Well, if you ask Google, training is learning good values for all weights and biases from labeled examples, for example. I mean, it's quite sophisticated in a way definition, but I hate that, to be honest. So if you were to ask myself, training is all about, you know, like making a guess, seeing how wrong you are, and then repeating until you're not wrong anymore. And that's usually true for most of what we do in programming anyway. So we try something, it works or not, and then we improve, right? And that's really what training is all about. So you make assumption based on some crazy values, you see how wrong you guesstimated, and then you change the values and improve. And for example, for our data set, this would be the input to predict. So these are the vectors. These are the input vectors with the 4 dimensions that I mentioned for each species. And basically for these, we actually want to predict to which family, which one of them belongs. You can just use one vector, you can use multiple, whatever you want. And basically, if you check, yeah, so these are the features, as I said. And if you check the output, basically this is what our model did. So it predicted that first one is, so first couple of them are of family Setosa or Setosa, whatever, the rest is stuff. And that's actually pretty much it about the training and testing. As I told you, you can get a long way without not having any idea what you're doing. And you can actually get pretty good results. I think these are quite good results as they are. Now, this whole process that I was talking to you, that I was talking about is called data classification. Because you have like a labeled data set. Basically, you have some input features, columns, whatever you want to call them, and you have a label that you want that each one belongs to, right? And what you're doing is actually you're classifying based on this input data. The input vector belongs to this class. And in case of the iris data set, we had like I think 3 classes, right? Setosa, Virginica, and whatever. Now, basically, vectors and labels, right? Two important things to understand. Now, give me just 1 second. Why am I talking about data classification? I'm talking about data classification because what recommendation systems are, they're just a niche, so to say, of data classification, believe it or not. So, again, pay attention to this picture. So in a typical data classification scenario, we have input features, we have this matrix, this data set that is fully specified, and we have one column that represents the output label that we want to guess. Well, not guess, to classify. When it comes to recommendation systems, it's similar and yet different thing. When it comes to recommendation systems, you usually actually have incomplete matrix. You have only some values. Just imagine that each row, each vector is actually a user, a Netflix user, for example, and columns are movies, you know, and I would presume that it's hard to find a user that rated all movies, right? I mean, most of the users rate like, I don't know, 10, 20, 50 out of how many movies there are on Netflix, I have no idea, right? So you have this pretty much, I'm trying not to use the original word, pretty unspecified matrix, so to say, for now. And this could be one example, you know. It's obviously like a smaller one, but basically you only have some values specified, but not the others, right? I hope that makes sense. Whereas in data classification, you actually have a clear separation between like input values and the output class, right? This thing right here is called a sparse matrix. You might have heard about it, you might have not, but that's the official term. And the official term exists for 2 reasons, so that you can actually tell somebody, well, we're doing stuff with sparse matrix. That's one, and for 2, there are some algorithms that work better with sparse matrices, as we will see. Now, back to this example of data classification versus recommendation systems. If I were to give you this matrix, and if I were to ask you like which user is similar to user number 1, user with ID 1, right? Basically, you can look at the matrix and just tell me, well, based on the ratings, the user with ID 6 seems to have rated similar movies with similar ratings, right? So you can figure out, yeah, these 2 vectors seem to be similar, right? That's quite an easy way to actually find a similar user, and based on that, we can actually conclude, since, well, there is this similar users, so if this user is like me, there is a high chance that this user has rated the movie, that I would rate the movies just like this user did. And if you want to do that on a grander scale, you can just go back to if you go back to this example of people that you're hanging out with. So the whole point is that basically your ratings are probably going to be similar to the users that you are similar to. And if you go back 1 step backward, the way to measure the similarity is using the cosine similarity. And that's exactly what I'm going to use here to show you how you can build this very basic recommendation system, which is like find similar users, and based on that, deduce the values that inherit the values, whatever that I might, you know, because once again, if we start from this matrix, we can deduce that I would probably dislike Peaky Blinders and I would likely love Money Heist, which is basically, I just recommended you Money Heist, and I definitely won't recommend you the Peaky Blinders, right? The whole thing is just to make it on a grander scale. Instantiating the data set, you just instantiate the unlabeled data set, because this time you're working with there are no labels there, right? And as you can see, there are 610 users. So I downloaded this movie lens data set. It's just publicly available data set with 600 users and 9,000, almost 10,000 movies. Basically, each row is a user, each column is a movie. And let's say that I want to make recommendation for user with ID number 5, just for the fun of it, right? And as you can see, this user has rated 300 movies out of 9,000, whatever. So that's a pretty sparse. He's lacking like 9,000 something rows, 9,000 something ratings, like are not filled. So what do you do? What would you do actually? So basically, you go back to everything that I was talking about, which I hope you didn't slip over, which is basically take all users, calculate the cosine similarity, find users that are similar to myself, and then based on that, we will see like deduce the values of the similar movies that they all rated, right? Now, one thing to notice, it's actually missing here, there is in Rubik's ML, there is a class called safe cosine distance, which pretty much just ignores the values that are not present in both vectors. So it actually focuses only on the values that you and another user that you're being compared to have rated, right? So we deduce that user number 42 is actually most similar to us, and then the user number 57, whatever, and stuff like that. Now that we have a list of users that are similar to us, it might look a bit challenging, but the whole point is basically iterate through users, find the movies that similar users have rated and I haven't, and just basically increase the number of, for every hit, increase the number, you know. And at the end of the day, like just sort that array, found the movies that were liked the most by the most similar users and that I haven't watched. And that's pretty, like that's right there. These are some very basic recommendations for this user. And again, you ended up with a very basic recommendation system. And it's simple, yes, and it might look slow, and it is a bit slow, but this provides a very good basic. And this whole concept here is called collaborative filtering. It's called collaborative because you actually rely on other users, or like it's called user-user, basically collaborative filtering, because if you want to recommend something to myself, I'm going to find users similar to myself, so it's user-user, and then based on their likeness, whatever, recommend stuff for myself. There is also item-based collaborative filtering, where you take a movie, let's say that you want to recommend some movie for me. So you basically take some movie that I liked, then find similar movies to that movie, and there is high chance that I might like them as well, right? So it's called collaborative filtering because it relies on collaboration between vectors. Now, back to this example and back to why I made such a big intro with data classification. So this all had nothing to do with data classification, right? Now, there is another way which turned out to be a more sophisticated version of it, was what won the Netflix competition eventually. There is a way to go from the right-hand matrix to the left-hand matrix. Is it right for you? Yeah. Wait, I just realized that you don't see the colors actually. Jesus Christ, there is no gray color here. I just figured that. What? One sec. You don't see the gray colors on the right-hand side. Who? You don't see anything actually. Huh? But, oh wait, but this, because, oh Jesus Christ. There is a gray color on the right-hand side and I just feel, huh? Oh well, because it's actually important to see this. I just feel, because I see the gray color here. Give me just one sec. No, not this one. Let me show you something else. No? Huh! Oh, Jesus Christ. Oh, that sucks. Oh, well, what can I tell you? Well, I will have to, well, so basically, what you don't see here, unfortunately, is that what you don't see here is that some of the boxes are gray. You know, like this one is gray, and I think this one is gray, whereas here, these ones are gray. So, yeah, so basically, this is a fully specified matrix where all values are specified, whereas here, only some values are specified. So just imagine that every second row, they are randomly filled. Let me go back to the old image to give you an idea, because it's really important to actually, I just figured, oh, you don't see it even here. Wow. You see a bit of gray, right? I mean, you're like, so the point is, there is a way to go from this matrix to a fully specified matrix. Like you can go from this sparse matrix to a matrix that has all values filled. And luckily, my next image won't rely on the colors. So yeah, that sucks. I apologize. I should have checked the here as well. So yeah. There is a way to go from unspecified to specified, and this way is called dimensionality reduction. And as I told you, it turned out to be one of the winning algorithms, and there is a white paper actually published, like the winners. And the winners were actually like independent teams that eventually joined together to create like a unified super recommendation, whatever team. It's an amazing thing, but it's hard it's hard. I would need a whole presentation to show you how it works, but you can actually understand the point really easily. So dimensionality reduction is all about going from this colorless matrix to the one below, right? Now, one thing to notice, luckily you don't need colors to notice. One thing that you can notice is that the upper hand matrix, it doesn't even have a shape like this. The upper hand matrix has 1,000 columns, and the one below has only 4 columns. What we did is actually we reduced the dimensionality of this matrix in order to end up with this fully specified matrix. And there are 2 algorithms that you can check them out, you can understand them, but the math behind them might be a bit trickier, but it's actually, there are some cool resources that I'll show you at the end to help you understand it. And they're called principal component analysis and singular value decomposition. And the second one turned out to be the one used in Netflix, which basically made them, they won the $1 million prize, and they boosted like recommendations for by 10%, I think. And again, I have this unfortunate image that doesn't give you anything, sadly. So I'll just pass over this slide. So I'll show you an example of PCA, principal component analysis, but it's absolutely the same with singular value decomposition. Principal component analysis, I'll try actually to give you a simple way to understand it. Basically, it takes, well, let me put it differently. It works, I mean, it's a mathematical model, but mathematical, whatever it is actually, like algorithm, but it works on a basis that there are some hidden things there are some hidden assumptions in whatever your matrix is showing, and it actually tries to abuse that in order to bring those hidden things to basically, what you see below is those hidden things actually uncovered in a way. And for example, in terms of movies, I mean, you can have like 10,000 movies, but eventually you might like sci-fi and horror, but dislike romance and drama. That would be some underlying assumptions, and once it gets grasp of that, once it gets grasp that you put some positive ratings on sci-fi and horror and negative on drama and whatever, it can actually deduce a very small matrix where the columns could be, you know, like just genres, like horror, sci-fi, drama, and whatever, instead of the fully specified movies, and it brings values based on that. So that would be like a very simple layman description of PCA and SVD eventually. It boils down to finding those hidden assumptions, so to say. In case of PCA, it's actually eigenvectors. Now, this code here, which could be a bit scary, this is at this point, I actually realized that I hated PHP because it was, this Rubik's ML has so many things actually, but it's missing one crucial component, and that's actually you can't drop a column. For whatever reason, like you can't say, I want to remove this column. So basically, what you actually do, and this could be a bit challenging, so stay with me. What you actually do is you reduce your matrix. Let's use this one. So you reduce your matrix to a finite matrix, right? And then for each of these columns, you take each column and you think about, you make it a label, right? So for example, you remove feature 1 and you take feature 2, 3, and 4, you make those the features of your vector, and you make feature 1 the label that you want to predict. And then you train your model on that one. Then you do the same with feature number 2. You remove that one and you use the remaining 3 features to train your model. So basically, eventually, you end up with as many models as you have the columns. I mean, it could be a bit hard to grasp, but it's actually a really simple concept. So you reduce, you train your models, and then basically every time you want to recommend something, you just take the reduced version of the matrix and plug it into this. And this is the biggest point. Basically, once you reduce it to a fully specified matrix, you can use any data classification algorithm. And that's why I spent so much time talking about data classification, because you can go from unspecified matrix to a specified matrix and then use like 100 million algorithms that exist for data classification problem. And those are the 2 examples. The one was super simple, like collaborative filtering. Basically find similar users or similar items. The second one is this more advanced one, but it can boost your speed and recommendation results, and it can do enormous things. There is a third family of recommendation systems. It's called the content-based models. And this one is actually, I think, the easiest to understand. It basically boils down to the fact that if you can extract some features of your items that you're trying to recommend, you can just find the similar items based on those features. And I'll give you a specific example. For example, for the movie Terminator, there are actually these tags specified by users. So these are the features, right? So you can just take these tags and create a matrix based on these tags. And in this case, you completely wipe away the concept of user. You just focus on the content. You just focus on the items that you're trying to recommend. And why is this important? Because why would you want to remove the users, right? I mean, like you usually want to recommend something for the user. Well, there is one really interesting problem, which is like, what do you do with new users, right? Like when your user hasn't rated anything, you don't have anything to you can't reduce completely empty row to something useful, right? And basically this concept, this problem is actually called the problem of cold start. Like how do you cold start from nothing towards something to recommend? And if you ever went to Quora, Reddit, I don't know, maybe Instagram, you usually, like, as a new user, you get they usually ask you like about some content that you might like. because they use the content-based algorithms then to deduce something else that you might like. And yeah, I'm almost done as well. And that's also most of the stuff that I had prepared for you today. One really cool thing is that if you go to this URL, basically there is a whole conference that happens every year, rexis.acm.org. They are basically a conference dedicated only to research in recommendation systems, believe it or not. And there is so much material that it has been happening for the last, I don't know, 10, 20 years, whatever. And what's even cooler is that they actually have a YouTube channel where you can watch everything, all the talks and everything from this conference that is dedicated to recommendation systems. So my advice, if you're interested, check it out. It could be a cool resource. And with that, I'd actually like to thank you very much for your attention. I already told you, like my blog, Twitter, whatever. If you have a minute, I would really appreciate, because this is a rather new talk that I'm doing it only, well, this is actually the first official time I'm doing it. So I would appreciate if you scan this QR code. It will take you to a short survey where you can actually, like, I don't know, rate it and give me some feedback. And I'll be happy to answer any questions now if you have. I'm not sure if lack of questions means that the content was, wait. There you go.
Hi, thank you for the presentation.
You're welcome.
Great job. I have a question about storing trained network.
Storing what?
Storing this machine, state of machine. I can imagine that after training with, let's say, a lot of data, I would like to somehow store the state of the machine to not train it every time. Does RABXML has any methods? Could you?
They have their own format, which, for the sake of it, I can't remember now, but they literally have their own format for serializing the models to whatever, database, hard disk. So yes, it has. Yeah.
Thank you.
Yeah, you're welcome. More? There is one there. And you might be surprised, actually, for example, like deep learning and stuff like that, it's even easier to store than, for example, collaborative filtering, which is actually crazy. Like, the more complex it is, the easier it could be to store.
Have you compared Rubik's with Scikit benchmark?
No, no, but I mean, I could imagine Scikit, for example, or whatever, like PyTorch and stuff like that, being a bit faster. But one thing that you have to understand is, for example, in PHP, I mean, it was supported in 7.4, but PHP 8 has this concept of foreign function interface. So you can use the C functions directly, and Rubix actually does rely on some of those to I don't know, to work with data. And one thing that it doesn't do, which probably would make it a bit slower, is that in Scikit you have this concept where you can actually define, you can tell that each column in the matrix is of a specific type, so you make it a bit smaller, you know. In PHP this doesn't exist yet, for whatever reason, so I would imagine that for that reason it would be slower. But to be honest, on a grand scale, and this is a very important point, on a grand scale, if you have a team of people who are only doing PHP, I mean, why not just do it in PHP if it's not a massive difference? That's how I see it, at least. Does that answer your question? Maybe? It was a long answer, but
yeah,
I would guess it's faster. that's like a short version. Third time's the charm. I don't know. No? Then thank you very much once again.